Hello everyone, and a very warm welcome to Kognito Key. I'm so excited to have you here today. In this explainer, we're going to dive right into a super fascinating and honestly absolutely crucial topic in digital electronics. We are demystifying the octal number system.
Now, you might be wondering, we all know that digital circuits and computers really only understand one language, right? Binary. They run entirely on ones and zeros. So, it brings up a really great question. Why in the world would digital systems ever need an alternative to binary code? I mean, if binary is the native language of the machine, why do we need to learn a totally different number system?
Well, the core problem here is human error, especially when we're handling massive amounts of data. Take a look at this 9-bit binary string. Dealing with these endlessly repeating ones and zeros in real-world processing is, frankly, incredibly prone to error. It's so easy to mix up a 1 and a 0. But that exact same value can be represented by a neat, compact 3-digit octal number, 565. The octal system brilliantly compresses that long, messy string into a format that is exactly 1/3 the length, a real game changer.
Section 1. The octal system, a compact alternative.
Let's break it down. By definition, the octal number system is a base 8 system. This means its radix, or base, is exactly 8. Because of this, it uses only 8 distinct digits to express any possible number, and those are 0, 1, 2, 3, 4, 5, 6, and 7. And honestly, this brilliantly illustrates a crucial rule you absolutely must remember. You will never, ever see the digits 8 or 9 in an octal number. Literally every single value is expressed using only 0 through 7, no exceptions.
Now, just like our everyday decimal system uses positional values based on tens, right? The octal system relies on positional values based on powers of 8. So let's see how this builds. When you're looking at a number and you move to the left from the decimal point, the positional value increases in positive powers of 8, like 8 to the power of 0, 8 to the power of 1, and so on. Conversely, when you move to the right of the decimal point, the positional value decreases into negative powers of 8. It's basically the exact same logic we're already used to, just with a different base.
Section 2. Binary and octal easy conversions.
Okay, so the magic behind this conversion lies in a really simple mathematical truth. The base of the octal system is 8, which can mathematically be written as 2 raised to the power of 3, right? 2 cubed. Because of this perfect relationship, exactly one single octal digit maps perfectly to a group of 3 binary bits. This is exactly why, as we saw just a minute ago, the length of an octal number is always exactly 1/3 the length of its binary equivalent. They just fit together flawlessly. It's like puzzle pieces.
So shrinking a binary string into an octal number is actually a super simple 4-step process. First, you begin at the least significant bit right over on the far right, and you group those binary digits into sets of 3, moving left. Now, if your final group on the left is a little short, no worries. Just add zeros to complete it. Finally, write down the octal equivalent for each group, and boom, your long, unwieldy string is beautifully compressed.
And guess what? Converting from octal back to binary is just as straightforward. It's really just the exact reverse process. All you got to do is take each individual digit in your octal number and expand it back into its distinct 3-digit binary group. Even if there's a decimal point in your number, the rule stays exactly the same. Just unpack every single octal digit into 3 binary bits, and you've got your machine-ready string of ones and zeros. Easy peasy.
Section 3. Decimal and octal. Everyday math.
Moving right along, let's talk about everyday numbers. To convert a standard decimal number into an octal number, we use a fantastic little technique called the double-dabble method. Catchy, right? Here's how it works. Step 1, you take your decimal number and divide it by 8. Step 2, you continually divide the result by 8 until your quotient reaches 0. And step 3, and this is absolutely crucial, the most important part, you write down the remainders you generated along the way, but you must write them in reverse order from bottom to top. So the bottom remainder becomes your most significant bit, and the top is your least significant bit.
But hold on, what if your decimal number has a decimal point? Good question. For the whole number portion before the decimal, you just use the division method we literally just covered. But for the fractional part, after the decimal point, the rule flips entirely. Instead of dividing, you take that fractional number and successively multiply it by 8 to find your octal digits.
Okay, bringing it full circle. To convert octal back into everyday decimal form, we simply return to those positional values. Take every single digit of your octal number and multiply it by 8 raised to its specific positional power. Then you just add all those results together. That grand total right there, that's your exact decimal equivalent.
So, what does this all mean? This brings us right back to why learning this matters so much in the first place. As our source material beautifully summarizes, and I quote, "The output of the digital devices will be compact and error-free if an octal number is used for processing." By using the octal system, engineers and programmers can interact with complex digital electronics so much more efficiently. They completely avoid the headache and the huge potential for errors of handling massive, unwieldy binary strings. It is literally the ultimate digital shorthand.
And this actually brings up a really fascinating question for the future. As our technology pushes further into the realms of quantum computing, will we still rely on these binary and octal shortcuts, or is an entirely new numerical language waiting to be discovered? Something to think about, right? Anyway, thank you so much for choosing to learn with Kognito Key today. If you found this explainer helpful, please hit that subscribe button and definitely like and share this video with anyone else who loves understanding how technology actually works behind the scenes. Keep learning, stay curious, and I'll see you in the next one.